discussing RISC V Summit by Andes Technologies. It's a summit that is meant to popularize RISC V, also market products and services by a couple of companies that are in the RISC V space. The reason why we attend a summit like that is, one, to learn about RISC V, but also to understand what's happening in the compute space. We've said many times on this podcast that we believe wealth creation is highly correlated with compute. So whatever's happening, whatever new things are happening within the compute world, we believe will be giving us a sense for where the future is in terms of wealth creation. That's why we do this. The reason of this podcast is to give, the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. So this is a very good example of how we do research, how we hopefully can get a glimpse of where future wealth creation will happen. This is Not Even Wrong podcast. It's October 18th, 2022. This is Krim Telco. For the day, the fund is up 20 basis points. The market's up 1.1%. For the year, we're down 47.4%. The market's down 22%. We're underperforming by 25.4%. Just before I go into the conversation, tomorrow, Tesla earnings, hopefully a big event for us in terms of positive news, but it's a big event nevertheless, because we had a lot of negativity surrounding Tesla and its potential, particularly the sort of overshoot in inventories that is going to happen because they delivered less cars than they produced. Now, hopefully, this is just a matter of logistics and a little bit of China slowdown, but we'll hear about all these things. So the big news items that we want to gather from the Tesla call tomorrow, one is what's going on in China, and then what's happening in the rest of the world in terms of demand and how's production ramping up. And then the Cybertruck is one of the big products that we hopefully get soon. Earnings and margins should be strong, hopefully, and then guidance hopefully will consist within the 50% growth range that we expect from Tesla. Now let's talk about this particular summit. So RISC V is an open source development of an instruction set architecture, an ISA, that is based on RISC, which is sort of a modern version of what MIPS is, the former dean of Stanford who co-developed MIPS. And the idea of this reduced instruction set compute, or I don't know exactly what RISC stands for, but something with reduced instruction set, what it means is the following. Like, you have a very lean instruction set is the contract that the hardware has with the software. So it's within the stack. It's that part of the stack that connects software with hardware, and there's stuff under it, micro coding and then the gates and the transistors and all the physics that happen below, and above we have the compiler, most importantly, and then the software. So if you write a piece of software, for example, like we're working right now on microgrid with Andrej Karpathy, so we're writing a software that is helping us doing back propagation. So this kind of software, this algorithm, has to be compiled into something that the machine understands. And that is where the instruction set architecture kicks in. Because when you write the compiler for that particular software, in this case, we're using Python, which is a scripted language, so it goes down to C++ and then into a compiler and then down to the hardware level. In our case, we use a Mac, so we're using some Apple type CPU. What the ISA is very flexible, easy to use, and very modular way to organize this particular hierarchy. This is the key, and it is better than, let's say, what Intel has with x86, because it hasn't been evolved into all the use cases that a monolith like Intel had to deal with over the decades. Just a little anecdote also in, I think it's Andy Grove's book, one of his books, maybe The Paranoid Survive, I think. He talks about this particular decision that Intel made a long time ago to, instead of going with RISC, go with the opposite, so have very complicated instruction sets. Now, in simple terms, what is RISC versus what Intel is using, to just simplify? What is RISC? Let's say if you have a function called a sort function, like if you want to sort an array, so you have a certain an array which is a line of, let's say, numbers that is sorted in a let's say in a row, and each row has a particular number, and you want to sort this by size. You could potentially do this. You could have an instruction set that allows you to do that. So you just basically use this to say, okay, go sort, and then the sorting is kind of hard-coded into the hardware. You could have that, and or you could have a much more simple instruction set, and that's where RISC-V comes in, where you just allow addition, multiplication, not even multiplication, I think addition, shift, like that kind of thing, and then you build from there. So you build up all the complexity of whatever is needed from those very simple instructions. And the reason that is good is because, number one, it allows for a lot less power consumption because you're now a lot more flexible in how you implement, let's say, a multiplication. If you want to do machine learning, where you do, let's say, one-hot programming, let's say you turn an integer into a vector, and then you run that vector against a neural net. When you do these types of multiplications, and this was, by the way, one of the comments in the presentation today that I picked up, which is that the main workload of AI today is data movement and multiplication and accumulation, which is basically dot product calculation. So a lot of what we call machine learning is dot product multiplication. And that's just the nature of the way neural nets are designed. The architecture of modern neural net compute is dot product multiplication. And now you can then have a fairly flexible implementation of that in RISC-V because of the reduced instruction set. So it's not like you can have the same, of course, with something like Intel, but there you have these more monolithic instruction sets that you have to use to implement something like a neural net. And therefore, you might be either using too much power or not have enough performance, or all of the above. And that's, in essence, why this whole idea of RISC-V and this whole idea of using something new is even on the table. Another thing which is good about RISC-V, it's actually an open source project. Started out of Berkeley, and there's a company called Sci-Fi that we're following. They might do an IPO soon, so this is something that we could be actually investing also. This is not just research. Started out of Berkeley and has gained traction across Silicon Valley. This is a really good example of what Silicon Valley is all about. You have a university that starts with, let's say, rethinking an ISA, for example. So you rethink an ISA. And then you have the adoption across Silicon Valley. This is the power of Silicon Valley. This is the power of a community. When people are close to each other, when they listen to each other, they go to each other's conferences, they visit each other, they chit-chat, they literally have beers and barbecues and all of that stuff because they're all in the same place. And they start adopting this. Now, again, the reason that RISC-V is even on the table is because there are certain bottlenecks today that we're facing in the compute world, and it's really driven by two things. One is data movement, so movement from memory into or close to the CPU or to the CPU, and then it's the multiplication and accumulation, which is dot product multiplication. Those are the two main workloads that modern AI is all about. So if you can find better ways to architect those problems on the hardware side, you have a much better life. You have a much better performance in terms of power, in terms of cost, in terms of all these things. Tesla just had their AI day. They presented Dojo. This is the same problem. Now, Tesla didn't talk about RISC-V. I don't know how involved Tesla is in this particular case, but the point is all of these situations, all of these problems that, let's say, Tesla has, or that somebody like Microsoft has when they do AI in Azure, or when they do it for themselves for Bing, or whatever when Apple does AI for Siri or whatnot. All of these problems come down to data movement, multiplication, and accumulation. And can you do better with RISC-V? Well, sometimes you can, sometimes you can't. Now, RISC-V in particular is more popular right now in the so-called embedded space. What is the embedded space? That's compute in the car, compute in your earphone. Let's say there was a company, Sonic AI or something like that. They want to basically build an operating system for headphones. So they want to compete with Apple and the AirPods of Apple and build an operating system and have apps that you can download and use and all that kind of stuff. So there's a lot of stuff going on the sort of small remote embedded type space. But what RISC-V wants to do is scale all the way up to the cloud. And I think it's possible, and the people in this presentation have been very clear about that is actually a possibility. So the point for us is not necessarily to think too much about, let's say, what virtual software can do to accelerate the implementation of RISC-V. We're not a business that is trying to sell services or consulting or anything like that. What we really want to understand is just where is compute going, and that's why a conference like this is so useful, because these are people who are at the frontiers of novelty. And what's good about it is that we'll talk about the current problems that offer themselves to be used, to be solved in novel ways. This is the key. And again, of course, AI is one of the big workloads that everybody's talking about. So we have the embedded space, which tangentially, of course, concerns us in terms of Tesla, because Tesla is the mother of all embedded softwares within the car. We have things like how to improve data movement. This is something we got from Onur Mutlu's class, also in computer architecture. The bottleneck of today, the big bottlenecks are in data movement. So how can we move data faster from memory to the CPU, or not have it move at all, or have in-memory compute? A lot of that kind of stuff is what the research community is thinking about. We had an episode recently about the new paradigms of compute, which are incredibly important, because when there are new paradigms of compute like we have today, where we're rethinking our architecture, where RISC is becoming not just sort of a niche field, but it could be the next frontier of compute. And we can see that also in the stock prices of, let's say, Intel. Intel's x86 is definitely falling by the wayside because of all these new paradigms of compute. So this is not just some academic study or something we're doing here. This is real. And again, just having a new paradigm in compute means that we will have new products and services, new problems being solved. We will have the potential for new wealth creation. This is a conjecture we're happy to make, a conjecture that we think has a lot of substance, a lot more substance than something like saying, well, innovation is good and Silicon Valley will keep innovating. That doesn't mean much. But when we have these massive changes in compute, when we have a room full of maybe 100 people listening to an open source development of a new hardware architecture, in this case RISC-V, we know that compute is changing and new levels of compute are important. Now for us at Orange Capital Partners, the rubber meets the road, of course, when it comes to particularly physical AI, so self-driving cars, and also AI applied to biotech. By the way, a seminar we will visit in 2 days at Genentech within the context of Baylearn. So that will be something we monitor very closely. So those are the two big applications of machine learning that we are focused on. It's physical AI and biotech. Now on the biotech side, it's particularly important to solve the memory problem, because you have a lot of data that needs to be processed against each other. So you could have a lot of in-memory compute there, because let's say when you do things like sequencing or comparing genomes, there's a lot of simple math being done that could be done in memory compute. So this is the in-memory compute side. I think biotech can have some good applications. And then on the full self-drive sort of physical AI side, we're talking more about acceleration of, again, data movement, but also acceleration of multiply and accumulate, in other words, dot products. So to summarize this, this presentation we saw today it was in the context of RISC V, organized by Andes Technologies, a software IP company out of Taiwan that is focused on helping people transition from the common computer architectures to RISC V and implement them into their hardware. The main takeaway is that we are at a new paradigm of compute. This is clearly just the fact that RISC V is so popular is already testimony that there's a new paradigm of compute, that data movement and multiply and accumulate, in other words, dot products, are going to be the key for at least the next couple of years until we find maybe better ways to implement neural nets. But right now, this is really what is sort of the key of what the new paradigm of compute means, which is very, very close to what Karpati was talking about when he spoke about software 2.0. In other words, we're writing algorithms that morph themselves into solutions, and they're being fed by data. In other words, data is actually the programmer of today's software. And RISC V is part of the solution. It's not the only holy grail of solution. The other solutions that we have, like CUDA with the GPU technology of NVIDIA, and certainly also the existing tech around AMD and Intel is going to play a part. But RISC V is a new paradigm in compute. Excuse me, it's a testimony of new paradigm in compute that is exciting for us because, as like we said, new paradigms in compute means that there is a massive potential of wealth creation. Thank you.